and you have roughly 25 minutes.
Okay. So today I will be talking about parallelizable track pattern recognition in the high luminosity LHC condition. And thank you very much for having allowing me this opportunity to present some of the work that I've been working on. To slide 2. As an outline, I will briefly talk about the high luminosity LHC challenges and the importance of investigating novel algorithms to cope with the challenges that are ahead of us, and discuss parallel track building ideas for the CMS Phase 2 auto tracker, and then discuss some of the preliminary results that we have seen and sort of the outlook going forward. So slide 3. So the challenges of the tracking at high luminosity, if I were to set the stage, the track reconstruction for many of our experiments are very crucial for the physics output. But track reconstruction is generally time consuming, as you are probably all very aware of this. And for the high luminosity LHC, the problem is only getting worse. And as you can see from the right-hand side of the plot, it shows the time that it takes for a full reconstruction of an event and the amount of time that it takes for the track reconstruction shown in side by side. And you can see that the track reconstruction is generally dominant and is going up as things are going to the high luminosity. As you go through the pilot 140 and then when we reach pilot 200 or so, we'll be having so many vertices and so many interactions all at the same time, as you can see from the event display in the bottom left, that it'll cost us a lot of time to reconstruct all the tracks. This means that we may have to cut corners, or we may have to figure out a new way to speed things up so that given the budget that we can reconstruct all the tracks that we need. And we need to be very mindful of the fact that these choices or the innovations that we're making to do this is going to impact our physics performance, and will eventually have to keep in mind that it will not compromise the physics due to the large pileup, and then we have to be prepared for those things. So in slide 4, there are many novel algorithms on the horizon. I just took this photo from CERN recently, and as you can see that there's many novel ideas that are being investigated to address these issues in the high luminosity. So things that are, for example, in the very left-hand side with the MK fit, and it shows that there's the seedings and or per event or the per region, things are being vectorized to do the Kalman filter fits on a multi-core processors, or sometimes we have a different algorithm that are based more on the cellular automaton method and then are being parallelized in GPUs, or perhaps more aggressively, people are applying graph neural networks to reconstruct the tracks and is thinking about deploying on FPGAs or even on the cloud to parallelize it and then run it very fastly. And also there's also the dedicated custom hardware approaches, such as the Allen track or the track triggers in Atlas as well. And all of these things sort of have a common feature in the sense that many of the ways that they're approaching this problem is a keyword here is that we are parallelizing the algorithm so that many works can be done in a fast pace, so that we don't get swamped by the high luminosity LHC situations. So then I'm changing this set stage here for the CMS tracker in the high luminosity LHC situation, and let me show you why that this is sort of a unique opportunity in the high luminosity LHC for CMS, that it's worth investigating the parallel algorithm. So in the CMS tracker, the outer tracker consists of what's called a PT modules, a quote-unquote PT modules, which is two detector modules that are closely sandwiched together, and so that we can decide whether a track that's left, the hits that are left by the tracks are coming from a high PT tracks or coming from a low PT tracks. And this choice was driven mainly by the level 1 track trigger capability, that by having these modules, we should be able to read out the hits and then suppress the hits reading out from hits coming from a low PT tracks. So in the bottom right corner, there's a picture where it shows two modules that are sort of in parallel. And if a high PT track is going through, then it'll be leave the tracks hits in a nearby position, so that when you open up a search window that are consistent with a certain PT value, then you should one can restrict the number of hits to be being read out, because in the case of the low PT case, maybe the window is small enough that some of the hits that are left by the low PT would fail, and you can reject those hits. And so by having these two hits that are close to each other, what we call this in our case, in the context of our case, we call it the mini doublets. And once you form these mini doublets, one can then start looking at it with the lower multiplicity, and I'll come back to that a bit later. So and because these modules are making this decision about putting these two hits together, in each of these modules, forming these mini doublets can be done locally and can be highly parallelized. And so this enables a parallel algorithm in the outer tracker for the CMS, and this was a good opportunity to look into parallelizing the track building algorithm. So in slide 6, starting from I'm moving forward to how to build to explain how to build a track from the mini doublets. So if you imagine having two mini doublets between two modules, and it's the bottom left cartoon, I'm showing you two double layer PT modules shown in gray. And then there are the hits that are put together to form a mini doublet, which I'm showing in green circle. So if you put the two mini doublets together and then form a segment, you can start looking into how to build a track by linking the segments together. And this is also, again, can be done in parallel, because it only needs to know the nearest neighbor. The mini doublet has to only search its nearest neighbor to decide whether I want to make a segment or I don't want to make a segment. And this can all be done in parallel. And doing this at the outer tracker gives you a unique physics opportunity, because because it's in the outer tracker region, it does not have to depend on the inner tracker seedings, which is what a lot of the tracking algorithm is currently being dependent on. And so it doesn't have to depend on the inner tracker. And also, by relying on the segment linkings at the outer tracker, you can also naturally reconstruct the displaced tracks as well. So in slide 7, I'm going in a bit more detail about the linking between the segments. You can take the two segments, once the two segments are formed, you can connect these two through a geometrical argument. If the two segments are, for example, that are shown in the two top ones in here, if you consider the angles that it would create between the two segments and then plot the differences between the two angles, the links that are coming from between the true segments would appear in the peak in the middle, while the links that are not correct, for example, that's shown in the yellow segments versus the one in the bottom here in the blue, and they're not coming from a clear charge track trajectory, and then those would give you a large delta beta value and would show up as a combinatorial background on the bottom. So these segments, given that they have a direction, can be linked geometrically, and again, these things can be done in parallel. So in slide 8, the robustness of this approach by having these segment linking maybe becoming clear here that the segments are because the way that the segment linking is done, you can create many different kinds of segment linkings. And so, for example, I'm showing you a non-exhaustive list of possible track candidates that can be built out of putting the segments together. And so in the case in the very middle here, you can see that the 3 segments are being linked together to form a 3-segment track candidates, but also because it's linking between the segments through a certain gap, that you can link across the missing hits to allow a missing hits, or you can also allow some other missing hits, but connect with the pixel seeds that are, if available, from the inner tracker. So many of these kinds of combination can be done. And again, it only needs to know the nearest neighbor, and therefore the linking can be done all in parallel, which can potentially give you a speed up. Slide 9. This kind of segment linking has a lot of connection to other parallel algorithms. Once you build all the segments by putting the mini doublets together, the byproduct of the method is that it gives you a full graph connection between all the mini doublets. And so, for example, on the right-hand side, I'm showing you a screenshot from the PataTrack presentation from the last year Connecting the Dots workshop. And if you look at the bottom plot of the way that the hits are connected between them, this is sort of the basis of applying a graph neural network or using a cellular automaton method. And because once the connections are built, you can either do it in a geometrical way with the first principle, or you can also use a machine learning if you want. And so this algorithm being developed has many legs, and I think will be very beneficial in the future. Slide 10. So the benefits of this, the outer tracker parallel track building algorithm that I described is that it has a possible speed up by parallelizing everything, assuming that the combinatorial and the fix are under control. The traditional Kalman filter-based algorithm is, quite different. It's serial and sequential, although there are efforts going on to deploy it on a modern architecture. I have explained it with the MK-FIT. And this track building algorithm is naturally parallelizable, as I mentioned, and spectralizable. And also the outer tracker benefits are pretty clear that it's complementary to the pixel-based seeding track building. And many of the tracking that in CMS are critically dependent on the pixel health and the performance. And going forward in the future, this is also a one exposure that we can have. So if all of these work well, and it can also potentially benefit the HLT at the software trigger level if things are going, if things are, again, the combinatorial and the fix are under control, that is potentially could be used in the HLT as well for more extensive tracking, for example, targeting the displaced displaced tracks as well. So for today, let me show you a sort of a case study of what we have and what we've looked into. So as a start, we focused on no missing hits tracking the barrel outer tracker. So if you look at the outer tracker barrel region that's shown in the blue colors that I've mentioned here, there are 6 layers of these PT modules, and each of the PT modules will contain 2 hits each, and therefore, if you require that there's no missing hits in the outer tracker barrel region, then you would be requiring a 12 hits in total. And so for the target for today is a kind of the tracks that leaves all 12 hits. And so the track building that we're currently targeting is the one in the very first one in the very left-hand side that the cartoon is showing. This kind of track has the benefit of, again, not relying on the pixel track seeds, and it can be just built purely out of the outer tracker barrel. And the efficiency reported that I'm going to show for this studies, targeting these tracks as a sort of a denominator object that we want to target. The other kinds of tracks that can be built are for the future, and we're currently studying them to see what kind of impact that it can have. On slide 12, going back to the mini doublets to show the efficiency of building the mini doublets. So as I've explained, we're utilizing the PT modules and building the modules, mini doublets out of individual hits. The targeted PT threshold of the study is currently at 1 GeV. And this kind of, the mini doublets or the stubs using the PT modules is also being done with the custom hardware for the L1 track trigger for CMS in the future, but these are targeting the 2 GeV and above. And so we're targeting going down to 1 GeV to see how much we can do. Again, it only requires information on its own module, and so it can be done in a very parallel and very fast. And the top right plots of the 2 cases are showing you the efficiency versus the PT on the the outer tracker layer, and then the outermost one as an example of how it looks like. And you can see that the efficiency, good efficiency is achieved soon after the targeted threshold of a 1 GeV. then once the mini doublets, and the effects of these PT modules on the combinatorics, let me show you a couple of slides with the plots to illustrate the important the impact from these PT modules. So for example, on the left-hand side, I'm showing you all the hits that are shown in red are from pileup 200 TT bar events and are being deposited in the outer trackers. And there's a large number of hits that are being placed, so ranging from something like 6,000 to 36,000 hits in each of the layer. But once you then apply these mini doublet selections, as I've explained in slide 12, slide 14 shows you the mini doublet that are deposited in this same event once you select the 1 GB threshold and suppresses the hits that are left by the tracks that are less than 1 GB. Then you can see that the reduction factor between a number of mini doublets to something like number of hits is a factor of something like 3 to even up to about 7, and depending on the layers. And so this means that when you when you were to imagine connecting the hits, you would have a very large number of combinatorics that you have to consider in comparison to when you're trying to link the mini doublets, it would be much, much smaller. Then once you have these mini doublets, then we proceed to building a segment by connecting the 2 mini doublets. And in order to do this, what we have done is to create a module map built from a mu1 gun simulation events to aggregate the information between which modules are compatible. And so in the top left in the cartoon, I'm showing you a compatible modules between each of the layers. For example, the lines that I drew as a dashed line are indicating something like a 1 GeV tracks. And if you have a reference module that are shown in green, then you can imagine creating a module maps between the reference to the compatible modules shown in the blue that are within the 1 GeV acceptance. And the ones that are shown in the red would be incompatible, and there's no need to consider the mini doublets from the reference module to the mini doublets in the incompatible module to create a segment. So those are defining the region of interest to connect the segments. So once utilizing these module maps, then you connect the 2 mini doublets to form a segment. And then each of these mini doublets already has 2 hits each, which then you can create an angles to ask whether the angles between the mini doublets and then the angles between the segment to the beam spot, and all these angles between them are compatible with the 1 GeV threshold, and then can weed out some of these segments that are not true, and then accept only the segments that would be coming from a real consistent with the real track. And on the right hand side, I'm showing you the segments between, for example, layer 1 to 2, or layer 3 to 4, or 5 to 6, and again it shows a good efficiency being achieved soon after the 1 GeV targeted threshold. So then after the segments are formed, then you would have to try to now build more on top of it. What you can do is to then take one segment that is where the 2 mini doublets are put together, and then you consider a potential segment using utilizing the same module map concept to restrict your range of search. And then you take a potential segments that you want to connect that are shown in the dashed red line, and then apply geometrical arguments between the 2 segments. So for example, in the XY plane, you would require that the beta angles would have to be consistent, or in the case of the RZ plane, you would have to require that the pointing between the segment angles are consistent with what we expect from a true track. And these various angle compatibility between the segments and the linking are going to reduce your fake segment linking, and then accept only the true ones. And then you can form what we call a tracklet, which is 2 segments that are linked. Slide 17 shows as an example of how these delta beta distribution would look like in the tracklets. So for example, from the very left to the very right, I'm showing you tracklets that are connected between layer 1 and 2 and 3 and 4, or 2, 3, and 4, and 5, and etc. And I'm showing you a TT bar in the pileup 200 cases to illustrate that the clear peak is visible on top of the combinatorial background to be able to select the correct segment links. And the plots that are shown at the bottom is an n-1 plot. And so you would have to now actually, after seeing these peak, you would have to cut it on the window to accept only the true, not the only, but the true tracklets, and then reject many of the combinatorial backgrounds. Slide 18 shows the efficiency of such a link segment. And I'm showing you specifically the kind here on the left, where 1, 2, and 3, and 4 versus the layer 2, 3, 4, and 5, and 6 that are shown here for the muon events, and from the pions from the TT bar events of a pile 200, or the electrons from the TT bar events. And again, here the efficiencies are the ones that I've mentioned before, where we're targeting the ones that are traversing the barrel region and leaving no missing hits. And you can see that very nice efficiency is achieved soon after 1 GB targeted threshold as we've designed it to be. And the tracklets efficiency shows a good value. Then to build a sort of a complete track candidate out of these tracklets, you can then take 2 tracklets and then put together to build a track candidate by requiring a share segment. So if you consider tracklet number 1, where you have the blue and the reds being linked, and if you have another tracklets where the red and the blue and the bottom 2 are linked, and if you consider again within the windows of the module maps, and then you ask whether they share a segment between the 2 tracklets, and if they do share a segment, then you would consider that as a built track candidate. And so this would be the track candidate that I've mentioned in the beginning, where we are trying to target to build. And in slide 20, we show you the efficiency of these track candidates. So now at this point, these track candidates contain 12 hits and is sort of pretty complete track. You can consider it as a pretty complete track. And as I mentioned before, the denominator currently only includes a track with the no missing hits present. But you can see that when the muons or the pions or the electron cases that she's shown, they show a very good efficiency as above the 1 GB threshold of a design targeted threshold. So this looks very promising to us. So in summary, in slide 21, as we enter the high luminosity situation, the reconstruction challenges are getting tougher and tougher. And so we must explore new algorithms to not cost any physics output. Currently, many of the promising novel algorithms are being developed, and something that is in common between all of these algorithms is that the keyword here, I believe, is the parallel. And here, I think, we've studied a sort of a parallel track building algorithm for the outer tracker geometry in the CMS. And this sort of algorithm that is using the outer tracker has a very natural benefits that comes from parallelization and vectorization, and also have benefits for not relying on the inner tracker, and have being able to naturally also target the displaced tracks as well. So I've shown you a preliminary barrel region only segment linking algorithm, and the track candidates that are built out of 12 hits show very good efficiency. And we going forward, we would like to investigate this more and build it up to cover all of the detectors. So that's all I have for today.
Thank you very much. This sounds and looks very promising. Do we have questions or comments?
Hey, this is Shovek. I have a question. Sorry, should I raise my hand? I don't know how to raise my hand here.
It's okay, just go ahead.
Sorry, so on slide, this is 17, you talk about the delta beta distribution, and suddenly I realize you're on the top left, you have the theta angle or the pseudo rapidity angle, but on the other plots you have the phi angle. So which angle is actually delta beta? Is it along the azimuthal or along the longitudinal, this one?
It's the one in the XY plane.
Okay. So then that should not give you any information along the RZ plane, no?
It does not. And so, but given that the segments are between the 2 mini doublets, what we're saying is that we're not applying only one cut, but we're applying all the geometrical cuts that we can apply. So for example, in the XY plane, we would be applying a delta beta cut, and also in the RZ plane, you would require that the lines are consistent between in the RZ plane as well.
I see. So one other broad general question. This seems very similar in some flavor to the CMS tracklet method of track triggering, which was initiated at Cornell by Anders Rid. Now, is there any fundamental difference between that tracklet method and this that I'm missing here? Or?
So the case with the L1 track trigger, I believe that's what you're referring to. Right. They first build the tracklets and form a segment, but then they do a extrapolation all the way to the rest of the 4 layers, and then pick up the hits together. And so, in some senses, there's 2 steps in the stages, and you have to rely on the first stubs that you have, the segments that you have, and then be able to pick up all the rest of the 4 layers correctly. Whereas in this case, we're parallelizing in each step so that we don't rely on the accuracy of the one segment, but be able to connect with each of these layers separately and then prune things out in steps.
I see.
And also, the L1 track trigger targets the 2G and above, and so the tracks are a bit more straighter. And this is what we're trying to here is to, for a general purpose algorithm, targeting down to 1 GeV, potentially targeting first with the reconstruction to address the reconstruction offline, and whether or not it'll be also useful in the online is something that we have to study.
Okay, thank you. That answers all my questions.
Do we have another question? If we don't have another immediate question, then thank you for the talk, and also thanks for everybody who presented. I'm fully aware, as we all are, it's a little bit of a new situation. I mean, most of us are very used to online meetings, but not trying it in a conference style. So the